Hi guys, and welcome to another video. This week we're going to be continuing on with our mini-series about linear regression, and the topic of this week is beyond straight lines. So we're going to be thinking about how we can start to fit data which has a more complicated relationship than just a simple linear fit. So, as a reminder of what we've done so far, we have encountered this situation where we have gone out and collected some X data, and we've also got an associated set of Y data. Now the X data represents our independent variables and our Y data represents our dependent variables. So the idea is, once we've measured all of these XY pairs, if I give you a new X without a Y, can you tell me what the best guess for that value of Y should be? Now we've been so far just looking at this idea of a simple linear fit. So that means fitting functions that have this kind of form, where the function of x, or i.e. our prediction of x, is going to be a linear function of x, which means it's x multiplied by some constant, gradient, plus an intercept, another constant c. So this model has two parameters, m and c, and from those, if we go out and sort of collect all this data, our x's and y's, then we could find the best values for m and c. So you can kind of see here, this is the type of situation we have. So we've gone out and collected all of these points. Each one has an x value and a y value. And we've got a bunch of different points here. And then we've found the best value of m and c. We found the best line that goes through this data. So then if I come along and say, okay, I want to know what the best guess for y is when x is 10, we just go up to where this line is, and it's whatever that is, 27-ish. Okay, but what if we have a situation where our data is clearly not a straight line? So we can look at something like this here, and we can straight away see that a line is no longer going to accurately predict or accurately describe this collected data. There's clearly a more complicated relationship going on. So we're going to have to come up with models that are more flexible than just simple lines. Now, one way that we can do this is by introducing the idea of a polynomial. So what is a polynomial? Well, you may have encountered some simple polynomials at school in your maths classes, but the idea is basically this. We introduce higher orders of x. So we have for example, a quadratic equation where we have some constant plus something in x and something in x squared. So here it's just 1 plus 1x plus 1x squared. Here we've got 2 plus 1x minus 2x squared. But we can keep this going, so we can go up to a cubic, for example, and this here is an example of a cubic polynomial, whereas this was a quadratic. So here we've got a constant term, an x squared term, and an x cubed term. And of course, we can just keep this going. We can go to x4, 5, 6, whatever you like. Now, once we start introducing these higher order terms, we are going to no longer have a straight line. As x varies, the function f of x is no longer going to vary in a linear way. There's going to be some kind of curved nature to it. So let's take a look at the idea of a quadratic polynomial. So in general, a quadratic polynomial is described by three numbers, a, b, and c. So we've got a constant, and then we've got something multiplying x, then we've got something multiplying x squared. So if I give you three numbers, say 1, 2, 3, or 5, 9, minus 12, each kind of triple, each sort of set of three numbers will describe a different polynomial, a different quadratic polynomial. And they will, in general, be curved. So let's just take a look here. So what are we doing here? We're just going to import NumPy and Matplotlib. We're also going to run this Matplotlib notebook thing and set some NumPy print options. And we're going to run that notebook thing again. This we don't need to worry about. We can actually get rid of that. And here we're just going to import the first graph that I've written, which is an interactive graph, so we can see what's going on with these quadratics. Okay, so you can see here that we have something that's no longer straight. So this is a quadratic that is described by these three parameters, a, b, and c. And you can see that by varying these parameters, we can change the curve. So if we change A, the first parameter, you can see that that is just shifting the graph up and down. So that's fairly easy to understand. Now B, that's the linear term. You can see as we change this, the kind of graph is changing as well. And as B gets strong, it has this kind of upward sloping nature, and as B gets smaller, it has this downward sloping nature. So as B is negative, it kind of slopes downwards, and as B is positive, it slopes upwards. And this C here sort of shows us this kind of curvature. So as C gets really high, we have this thing that sort of tends to curve up like a sort of U shape, and as we make C go negative, we have a thing that tends to curve down in a kind of N shape. Okay, so you can see that any sort of three variables that we set is going to define a different graph here. Cool. So the idea would be, if we had gone out and collected some data, then we would be able to find the values of A, B, and C that kind of form a graph which best follows the curve of our data. Now, how do we do that in practice? Well, we're going to just go back to this idea of our sort of error, our fitting error. So consider this. So for the first input data point that we've collected, so remember that our data comes in pairs x1, y1, x2, y2. So just taking a single point, x1, if we are given some values for A, B, and C, then our prediction for what the output should be at that value of x1 is going to be A plus bx1 plus cx squared. Plus cx1 squared. But we know that we've actually really measured a value of y1. So we have a true measured value of y1, and we have a prediction of f of x1. So the difference between our observed value and our predicted value is going to be y1 minus f of x1. And if we sort of set that out here, it's going to be y1 minus a plus bx1 plus cx1 squared. And then we're going to square this because, all we care about is the difference. We don't care if it's positive or negative. We just care about the difference. So we're going to square that so that a negative becomes a positive. And then what we're going to do is we're going to do that for every single data point. So we're going to sum over I. So this sigma notation here means we're going to sum from I equals 1 until I equals n of yi minus f of xi squared. So that's going to be y1 minus f of x1 squared plus y2 minus f of x2 squared. And we're going to do that for all of our data points, and we're going to add that up. And then our definition of the best value of A, B, and C will be the values that minimize this total error. Okay, so to start seeing how we can solve this in practice, we're going to create some artificial data. Now, hopefully you remember from the notebook before. If not, you can just go back and check that. We kind of went through the way that you might be able to create artificial data of this nature. So the first thing we're going to do is create this X data array. So this is going to be the array that holds our points x1, x2, x3, x4, x5, all the way up to xn. So what you need to do for this first exercise here is to select a x value at which this starts. So, our data could go from, say, x equals 10 to x equals 30. So you want to set as x start, which is just going to be a number, and xn, which is just going to be a number, and then the number of x observations that you're going to take. So this could be 10, 20, 30, whatever, just the number of the number of kind of observations of xy pairs that you have. And then we're going to create a kind of linearly spaced array of x observations by using numpy or np.linspace. And if you can't remember how exactly to use that function, you can always just insert a cell and go np.linspace and then hit question mark and hit enter, and then you'll get some information about how to use that with hopefully some examples at the bottom as well. Great, so we'll get rid of that. So your first exercise is just to create this X data array. Okay, so now we're going to set some values for A, B, and C. So these are going to be the real values that are actually driving the underlying relationship of this curve. So you can set them to be anything you like. Just set them to be between roughly -10 and 10. Doesn't matter too much. So if you set these, you will then be able to make the y array. So this is going to be the corresponding y points as a plus b times the x data array plus c times the x data array squared. Now, remember that a is just a constant, and when we do b times x data, this whole thing here is going to be an array, because x data is an array. So b times x data means basically b multiplied by each element of x data. So this whole thing is going to be an array. And when we add a constant to an array, to a NumPy array, that also gives us an array. So this is an array, and that means that this is an array, which also means that this is an array, because what happens is you just add the constant to every element in this array. Okay, so this whole thing is now an array, and we're adding that to c times x data squared. So x data squared is also going to be an array, because when we do an array squared, you basically just square each element of the array, and then we're multiplying each of those by c, and then we're adding these two arrays together. So hopefully you can see from that this thing that we're going to get out at the end, we don't actually need any of these brackets, but what we're going to get out at the end, y true, is going to be an array. It's going to have the exact same length as x data, and each element in this y array is going to be a plus b times the corresponding point in the x array plus c times the corresponding point in the x array squared. Okay. Next thing that we're going to do, which we also did in the last notebook, is we're going to create some random noise. So this array that we've just created here, this y true, that's actually going to look like a perfect quadratic polynomial, right? Because there's no randomness. There's just this, that every point is exactly a plus b times x plus c times x squared. But we don't want that. We want to kind of simulate a situation where we don't have a perfect relationship. We just have a kind of rough relationship and some kind of randomness in the data as well. So the way that we're going to simulate that is by using this numpy.random.normal function, which you used in the last notebook. So again, if you can't remember how to use it, you can either look back in that notebook or you can type it into a cell with a question mark and hit enter, and it'll give you some information on how to use it. But the idea is we want to create an array where each element in that array is a random number that's drawn from a normal distribution, and the mean should be 0, and the standard deviation sigma should be some number, some non-zero number greater than 0. And then we'll store that. So sigma is just going to be a number which you can set. Noise is going to be this array which you can set from this numpy.random.normal function. And then the y data that we're actually going to observe is simply going to be the true underlying y data, which is this array, plus the noise array. So that way we're going to sort of simulate this randomness where every single point is going to be kind of close to what it should be in this underlying relationship, but it's going to have some random noise added to it. And because this random noise has a mean of 0, where each one of these the elements of this array will have mean 0, it means that there's an equal chance that you'll be sort of adding to this or taking away from this. Okay, so in the next exercise, use the function plt.scatter to take a look at what you've just created. Again, if you need help with this function, you can use the question mark thing, or you can go back and look at some previous notebooks. But you're going to need to scatter x data and y data and just take a look at the kind of relationship that you've observed. If you're not happy with it, if you think it looks too random or it looks too perfect, go back and change some of these values. You can change sigma, you can change A, B, and C if you want as well. Just get something that you think is reasonable, and then you'll be ready to move on. One thing that I should say as well is that remember when you're making this noise array that it needs to be of the same length as your X array and your Y array. Okay, right. So the next thing that we need to talk about before we can get on to exactly how we're going to solve this problem is the idea of linear algebra. Now, linear algebra is a incredibly widespread piece of mathematics that you will find popping up all over the place in incredibly useful situations. So everywhere in engineering, physics, chemistry, biology even, all sorts of mathematics from quantum mechanics to, machine learning to artificial intelligence. Linear algebra is absolutely everywhere. And I say that because when you first look at linear algebra, it seems a little bit arbitrary. I remember kind of learning this for the first time and thinking, this all just seems slightly strange and contrived, and it takes a long time to appreciate the reason why these things are useful. So that said, let's just talk about what linear algebra is. So linear algebra is basically the study of vectors and matrices. Now, you will possibly have come across vectors before. I think it's unlikely that you will have come across matrices before. So the idea of a vector, talk about that first, is basically you could think of it as just a list of a sort of 1D list of numbers. People sometimes also like to think of it as a kind of arrow pointing in space. So if you're doing physics, you might often visualize things like force and acceleration and velocity as an arrow that points in some direction in 2D or 3D space. That's also fine, but that basically just limits you to the case where your vector has 2 or 3 elements. But as computer scientists, we like to have more flexibility and be more general. So we actually just think of a vector as not necessarily an arrow that you can picture, but just a list of numbers. And the dimension of that vector space is defined by the number of elements in that vector. So a vector with 3 numbers in it is going to be a 3D vector. A vector with 5 numbers is a 5D vector, etc., etc. But it basically is just that. It's just a column of numbers. So what can we do with these vectors? Well, for example, if you have 2 vectors that are of the same length, then you can add them together. And the way that you do that is pretty simple. You just add each of the elements together in turn, like this. So if we have a vector u and a vector v, then we add them together. The first element of this new vector is going to be u1 plus v1. The second element is going to be u2 plus v2, u3 plus v3, all the way up to un plus vn. And that might seem familiar because that's basically exactly how NumPy arrays work. So if you had a NumPy array called u, which had length 5, and you had a NumPy array called v, which had length 5, you can just go u plus v, and you'll get a new array slash vector of length 5, where each element will be the corresponding element of those 2 vectors added together. So that's pretty good. And similarly, you can do subtraction. So you take away v in the exact same way. Is just going to be element-wise. So the first element of this new vector will be u1 minus v1, etc., etc., down to un minus vn. Okay, so something that you may not have seen before is called the vector transpose. So we tend to think of vectors in a mathematical sense as kind of being standing up tall. So they're kind of columns. And then the transpose of a vector is basically just flipping it 90 degrees onto its side. So it's basically now just a vector that goes v1, v2, v3 to vn, but kind of horizontally, like across. And the way that we denote this transpose is by doing a little kind of t up at the top, above the vector. Now, if we have a vector transposed multiplied by a regular vector, and they're both of the same length, so this is a situation like this. So this is our transposed vector, this is our regular vector. The meaning of this u transpose v is basically that you take each of the elements and multiply them together and add them up. So it's going to be u1 times v1 plus u2 times v2 plus u3 times v3 all the way up to un times vn. So you can see that here, u1 v1, u2 v2 all the way to un vn. So you can see from this, hopefully it's clear that u transpose v is the exact same thing as v transpose u. And also this only works, as is the case with addition and subtraction, this only works if the two vectors are of the same length. So this thing is sometimes called the inner product or the dot product of two vectors. So let's just take some examples here. So if we have u and v are these two vectors here, we can add them together. Hopefully you can see how that's done. We can subtract them in the same way, and we can do the we can sort of do the inner product or dot product between these two vectors. Hopefully you can see how that works. Okay, so hopefully that wasn't too much of a struggle. So the next thing that we're going to talk about is something that I'm sure for almost all of you will be new, and that is the idea of matrices. Now, matrices are basically, if you think of vectors as a line of numbers, matrices are basically a rectangle of numbers. Okay, so a matrix A is defined as this kind of block, right? A block of numbers, which has a height n in this case and a width m. So it has basically n times m elements, and they're kind of ordered like this. So it goes A11, A12, all the way up to A1m, and down here it goes A11, A21, all the way down to AN1. So you can think of a matrix in two ways, and both of them can be useful. The first way that you can think about a matrix is that it's basically just a bunch of horizontal vectors stacked on top of each other. So that's what we're kind of depicting in this picture here. So you can think of this whole top row as being a vector, and this next row as also being a vector, and we're basically going to have n vectors. So we've got our R1 here, R for row, so we've got row 1, row 2, all the way down to row n. You can kind of think of this as a transposed vector, right? So that's what this little t is saying. It's kind of like a horizontal vector, which we said is like a transposed vector. And then similarly, you could also think of it as being like m regular vectors, just sort of standing next to each other. So we've got C1 for column 1, column 2, all the way up to column m. So this would be column 1, this would be column 2, and this would be all the way up to column m. So what can we do with matrices? Well, a matrix is basically can be used to multiply a vector. And now what that does is, if a matrix multiplies a vector, what we get out of the other side is another vector. So a matrix times a vector gives us a vector. And there's kind of two equivalent ways that you can kind of think about how you calculate this thing. So the first one is that each element in this new vector that we're creating via this product is going to be the dot product between each of the matrix rows and the vector that we're multiplying. So in this case, we're multiplying a vector called v, and we are multiplying it by a matrix A, and we're going to do the first element of this new vector that we are creating is going to be the dot product between v and this row. Now the second element is going to be the dot product between v and this row, and so on until we get to the nth element of this new vector, which is going to be the dot product between this vector and the final row. So one thing that's important to note, and that you can probably notice here, is that the vector that we're going to get out of the other end is going to have n entries, right? Because this matrix had n rows, and we're going to do it with every single one of the rows. So it's going to be a vector that has n elements. And this vector, if it's going to be multiplying on this matrix, if we're going to be doing this dot product rather between this vector and each row of this matrix, then each row of this matrix and this vector better be of the same length. So if we're talking about this vector here, this matrix here, A, which has a width of m, then this vector V must have a height of m. So A is basically taking a vector which has length m and producing a new vector which has length n. Now that's one way of thinking about it. Now another totally equivalent way of thinking about it is that you are basically taking each element of this vector m, and you are basically going to add up all of these columns in the vector in the matrix A, and you're going to sort of multiply it by each element of this vector you're multiplying. So it's going to be a sort of weighted sum of the columns of A, where they're weighted by the corresponding element of the vector that we're multiplying. So in this case, it's going to be, if we're doing A times V, and A has columns C1, C2, all the way up to Cm, then we are going to, and we're multiplying that by this vector, which has elements V1, V2, all the way to Vm. So notice that because the width of this matrix is the same as the height of this vector, that's fine. We're going to have m here and m here. And then what we're going to get out at the end is basically V1 times C1 plus V2 times C2 plus Vm times Cm. Or rather, the first element of the vector multiplied by the first column plus the second element of the vector multiplied by the second column, blah, 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 plus, 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 all the way to the end. And it's maybe not clear to see why these two things are the same until you basically take an example. So let's do an example here. So this is our vector A. So it's got a width of 3 and a height of 4. And we're going to multiply that onto a vector V, which has a height of 3, which is fine because this has a width of 3 and that has a height of 3. So that's fine. We can do that. So the way that we're going to do that, so you could think of it as doing a kind of dot product first. So the dot product between this vector V is going to be 3 times 1 plus 2 times 2 plus 1 times 3. So that's what we're doing here. 3 times 1 plus 2 times 2 plus 1 times 3. And that's going to be 3 plus 4 plus 3 is going to be 10. So that's going to be the first element of this vector that we're getting out. Same for the second row. 3 times 2 plus 2 times 3 plus 1 times 4. 6, 6, 4 is 16. And same for this one, same for this one. So you can kind of see that each one of these is like a sort of dot product between the row and the vector. But you can also kind of see that this is sort of like, so we've got this first column, which is 1, 2, 3, 4. And we're sort of doing 3 multiplied by 1, 2, 3, 4. And that's the whole of this kind of, this whole thing is basically like we're multiplying 3 by this column. And this is like we're multiplying 2 by this second column, and multiplying 1 by this third column, and then basically adding them all up. So the first thing is this, and then this, and then this. And we're adding all of those together, and we're getting this vector out at the end. So hopefully you can kind of see from this why these two ways of looking at it are equivalent. Yeah, I think that's just kind of good to get your head around what exactly is going on here. Now, this is slightly confusing and it will take a little bit of time just to get your head around the mechanics of this. So that's fine, don't worry. But there we go, that is how you would do matrix vector multiplication by hand. But thankfully, we can just do this in Python pretty easily. And we can do that by using NumPy arrays to basically be these vectors and matrices. So for example, we can make a vector, which is just a NumPy array of 1, 2, 3. So we're going to say this is our vector v1, which is 1, 2, 3. And this is our vector v2, which is 5, 4, 3. And we can also make these matrices, right? By I'm not sure if we actually covered this in the NumPy lesson, but basically you can just make a 2D NumPy array by doing a sort of list of lists. So this whole thing is a list, and this is a list inside the list, this is another list inside the list, this is another list inside the list. Okay, so let's just run that. So we've got these vectors 1, 2, 3 and 5, 4, 3, and we've got these matrices 1, 2, 3, 4, 5, 6, 7, 8, 9 and blah blah blah. And we can basically do this matrix multiplication by using this handy at symbol. So for example, we can do the dot product between two vectors by doing v1 at v2. So if we run that, that's going to give us 22, because that's 5 times 1 plus 2 times 4 plus 3 times 3. So 5 plus 8 plus 9 is 22. And we can also do matrix vector products using the same notation. So we can do M1 matrix multiplied by V1 or M2 matrix multiplied by V2, and that's going to give us two vectors. And there they are. Great, so there are some exercises for you here. So go ahead and see if you can create this matrix in the language of Python and this vector and calculate their product. And then similarly, can you make another vector u, which is this, and then show that A matrix multiplied V plus A u is the same as A matrix multiplying V plus u. Okay, so why are we doing this? Well, basically, all of this linear algebra makes it quite easy to talk about much more general versions of regression. And the way that we're going to do that is this. So recall that we've collected our x and y data, and our x data is held in this kind of array that's going to be x1, x2, x3, all the way up to xn. And what we can do, and this might seem a bit strange why we'd want to do this, but if you bear with me, just follow along, you'll see why. We're going to create this matrix called X. Now this matrix is going to have a length of n, and it's going to have a width of 3. And the first column is going to be completely full of 1s. The second column is going to be basically just our collected X array. So it's going to be x1, x2, x3, all the way up to xn. And the third column is going to be x1 squared, x2 squared, x3 squared, all the way up to xn squared. Now we're going to consider a parameter vector called w, which is holding these numbers a, b, and c. So these numbers can be anything. We haven't decided what they are yet. We're just going to say they're called a, b, and c. And what happens if we multiply w by x? Well, we're doing this kind of matrix product here, and the thing that we're going to get out, you could think of it as doing the dot product between a, b, and c in this row. So it's going to be a times 1 plus b times x1 plus c times x1 squared. A times 1, which is just a, plus b times x2 plus c times x2 squared, going down, going down, and going down. And we're going to end up with a vector that basically has this form. And you can kind of see that if we have chosen a value of a, b, and c, then this vector is going to be the vector of predictions for a quadratic model. Because we said at the start that our prediction is basically going to be a times b times x plus c times x squared. So this thing, xw, is basically a vector of predictions. Now remember, we also had our vector of observations, which is going to be y1, y2, y3, all the way to yn. And if we subtract those from each other, so if we do y minus xw, we're basically going to have a vector of error. So each one of these is going to be basically the difference between our observation and our prediction. Now, if we do this whole vector transposed times itself, then we're basically going to just square each one of these elements and add them up, which is basically exactly what we wanted when we talked about the total error back up here. So we're talking about the total error, which is basically just the sum of yi minus a plus bxi plus cxi squared, all squared, and the sum of those. So that is basically I hope that you can see, you might need to pause the video and think about it, but I hope you can see that that is basically just the same as saying y minus xw transposed times y minus xw. So if we want to find the best vector of parameters w, then all we need to do is basically provide this matrix x and these observations y and say, from these, find me the w that minimizes this thing here. And that's a kind of slightly more clean way of describing our regression problem. But I hope you'll agree that it's an equivalent way. So if we want to solve this problem, we're going to have to construct this matrix X. Now, most of the rest of this notebook is basically just questions and exercises. So I'm going to just skip through it fairly quickly. Obviously, you're going to need to pause the video and fill in the exercises. So the idea is we're going to create this matrix X. So we're going to start with a blank matrix of the right shape, which is just going to be filled with zeros. So we can do that with np.zeros. Remember, if you need help with how these functions work, np.zeros, you have to pass a shape parameter. There's going to be some examples at the bottom here. So if you need any help on how to use that, you can just do that. So we're going to create first a blank np.zeros, but make sure that it has this shape, right? So it's going to have this shape, so it's got to have the number of observations that you made down this axis, and it's going to be 3 wide on this axis. Okay, and then the first thing we're going to do is populate the first column of X with 1s. So we're going to want to fill this whole column with 1s. Now, we can do that in one step. We don't have to loop through and say, you know, this element is 1, this element is 1, this element is 1. There's a way of telling NumPy to fill an entire column with 1s. And if you can't remember how to do that, take a look back at the NumPy video or in the previous, I'm pretty sure it came up in the previous notebook as well. And then we're going to populate the second column of X with our X data array. And the third column of X with our X data array squared. And then all that we're going to basically do is call the function np.lineal.leastsquare, and we're going to pass in X and Y. So remember, if you can't remember exactly how to use this, we'll just pop that in there, question mark. So this says np.lineal.leastsquare of A and B. It basically says it solves the equation AX equals B. So in this case, X is our vector of parameters. So A is going to be our matrix X, and B is going to be our vector of observations Y. So we want to pass in np.lineal.leastsquare of X and Y data. Okay, and then we can basically extract out from that the best fit. That's going to basically return us the best fit vector W, and print out the values that you get and have a look through those. And there's some more exercises for you to do here. I'll leave those to you. Finally, I just wanted to mention briefly that using this method, you can basically start to solve more general problems using the exact same kind of language. So for example, if we now wanted to solve a cubic, if we wanted to fit a cubic function to our data, then all that we need to do is basically just create this matrix X and add in another column and fill it with our X data cubed. And then do the exact same thing, and then we'll not only get the best A, B, and C, but we'll also get the best D, which multiplies an X cubed. So we can very easily begin to fit more complex functions by adding with basically very little extra work. So the final exercises there are basically just to repeat some of the stuff you've already done and see if you can fit a cubic polynomial. So each step is basically going to be very similar to something you've already done, and then just see if you can run through it and fit a cubic to the data. All right, that's all for this week. Thanks very much for listening, and I will see you next time.